Okay, let's get started. Today we are going to continue our discussion on lighting models. Last class, we took a look at two different lighting models, the Lambertian model and the Phong specular model. And the goal of these models is to model how light reflects off of different surfaces. In the case of the Lambertian model, this model is used to model light reflecting off of rough surfaces, where the light will roughly reflect back in all directions, roughly uniformly. The specular Phong model, on the other hand, is trying to model how light reflects off of smooth mirror-like surfaces. For these smooth specular reflections, light is going to be reflected back, concentrated along a specific reflection direction. Now, most of the surfaces that we see in the real world, they don't lie at these two extremes. Most surfaces are somewhere in between. They're not perfectly diffuse and they're not perfectly specular. And we refer to these surfaces as glossy surfaces. Now, to model specular reflections, we introduced this Phong specular model. And with this Phong model, we are going to calculate the intensity of the reflected light using the dot product between the reflection vector and the camera's view vector. For specular reflections, most of the reflected light will be concentrated along the reflection vector. So when the camera is close to the reflection vector, this is the configuration when the camera is going to see the most intense specular reflection. And this is represented by the dot product attaining its maximum value of 1. But as the camera moves away from the reflection vector, it's going to observe less and less of that specular reflection. And so the intensity of the specular reflection would decrease as we move further away from the reflection vector. There's also this shininess coefficient, which is used to control how concentrated, how sharp those specular reflections are. Surfaces with a high shininess value will have a very sharp specular reflection, while surfaces with a low shininess value will have a more diffuse specular reflection. So this Phong specular model is mainly used to model light reflected off of very smooth specular surfaces. But now if you want to model glossy reflections on surfaces that are not perfectly smooth or not perfectly diffuse, one way that we can go about modeling these glossy reflections is to simply combine the Phong specular model with the Lambertian diffuse model. So in this case, we now calculate our lighting model will now be a combination of 3 different components. First, we have the contribution CA from the ambient light. This is the hack that we mentioned before, where the ambient light is a uniform glow that illuminates all points in space uniformly from all directions. And this ambient light can be implemented by just taking some constant value, LA, which corresponds to the intensity of the ambient light. And then we just multiply that by the albedo, the surface reflectance of our material. Then next, we have the contribution from the diffuse model. This is implemented using the Lambertian diffuse model. And this represents light that's being reflected off of rough surfaces. And then finally, we have contribution CS from the specular model. And this can be implemented using the Phong specular model. So now we have these 3 different components from these different lighting models. And we'll just add them together to produce the final result, which will have both diffuse reflections and specular reflections. And this roughly represents how light might interact with a glossy surface where there's going to be some diffuse reflection and some specular reflection. Now, one thing to note with the way that we've combined these different lighting models is that the ambient light and the diffuse lighting model, the color of that reflected light is being modulated by the albedo, the surface reflectance of our material. But the specular reflection is not modulated by the albedo. So one reason why we might implement the lighting model in this way is that the diffuse reflection and the specular reflection, they model slightly different interactions between light and the surface. In the case of a diffuse reflection, this represents light that hits a rough surface, and some of the light might travel into the surface and then scatter inside the surface before being reflected back out into space. So when part of the light enters the surface, some of that light will be absorbed by the surface, and then some of that light will be reflected back into the scene. So in the case of diffuse reflection, this models what happens when some of the light is being absorbed by the surface. And the amount of light that is absorbed by the surface is determined by the albedo, by the surface reflectance of the material. Specular reflections, on the other hand, they represent mirror-like reflections where light hits the surface and then is directly reflected back out into the scene. For these mirror-like reflections, none of the light will be absorbed by the surface, and all of the light will be reflected directly back. So for specular reflections, this is not affected by the surface reflectance, by the albedo. Now, this is how we might combine these lighting models if we were trying to be physically correct. But in practice, it's often convenient to introduce different reflectance values, different albedo terms for each one of these different components of our lighting model. So Ka, Kd, and Ks here represent different albedo values for the ambient, diffuse, and specular components of our lighting model. And these different reflectance values can be specified by an artist, and this provides them with some additional control over the appearance of a particular material. So in practice, it's common to introduce different albedo values for each component of our lighting model. And for assignment 4, we'll be asking you to implement this second, slightly hackier version of the lighting model, where we will introduce these different reflectance terms for each component of our lighting model. So the top version might be more physically correct, but in practice, we'll implement the bottom version just to provide more control over the different lighting components. Okay. So any questions about this Phong reflection model? Okay. So now, one thing to note for this Phong model, right? Oh, right. Now, so one thing to note about this Phong reflection model is that similar to the diffuse model, we need to use this clamp to remove any negative reflectance, any negative values that we might get from the dot product inside our lighting model. So in the case of the diffuse model, this was to avoid negative illuminations whenever the light dips below the surface. In the case of the Phong model, we can get a negative dot product whenever the angle between the reflection vector and the view vector is greater than 90 degrees. Now, while the clamp might make sense for the Lambertian model, it can end up having some strange behaviors when we apply this clamp to the specular model. As an example of this, let's consider what happens with this particular configuration of the scene here. So here we have a reflection of a light on a very rough wooden floor surface. So for this rough surfaces, this corresponds to a surface with a low shininess value. So this is a very rough surface where we are going to get a very diffuse specular reflection. So rather than a very sharp and narrow specular highlight, we'll get a very diffuse highlight instead. And the thing that I want to highlight in this particular image is kind of this edge of the specular reflection. So for this rough surface, we end up seeing a very hard edge in the specular reflection, which is not really something that we would expect to see in the real world. Generally, we would expect to see a fairly gradual, smooth fall off whenever we see these specular highlights, especially for rough surfaces. But when we apply the Phong model to this rough wooden floor, we end up seeing these sharp fall-offs in the specular highlight. That's not particularly realistic. So to see what might be happening in this particular scene, let's take a look at the configuration of the scene that led to this artifact. Okay, so for this particular scene, it's created by a particular configuration of the light and the camera. So for this scene, we have a light that might be fairly far from the normal vector. So this light might be somewhat close to the surface. And when we reflect this light vector along the normal vector, we'll end up getting a reflection vector that looks roughly like this. Now, when we apply, suppose our camera is oriented somewhere along this particular direction. So with this particular configuration of the camera, the light vector, when we compute the dot product between the view vector and the reflection vector, this ends up leading to a negative value because the angle between the view vector and the reflection vector ends up being greater than 90 degrees. And as a result, we end up hitting the case where the clamp is going to kick into effect, where we are going to clamp all the negative dot product values to 0. Now, this helps to prevent negative illumination from our lighting model, but it can lead to unrealistic specular highlight when the shininess value is low. If the shininess value is very low, let's say some value fairly close to 0, this corresponds to a very rough surface with a very large diffuse specular highlight, which means that it's possible that even though the view vector is very far from the reflection vector, it's still possible that there's some specular reflection that's going to arrive at the camera at that particular direction. So if the diffuse reflection is very wide, it's possible that the camera might still see some of that diffuse reflection. But because of the way that the Phong model is implemented, we are always going to see a 0 diffuse reflection whenever the camera is more than 90 degrees away from the reflection vector. And this is not really consistent with what we observe in the real world. Now, in the case of the diffuse model, this clamp is not such an issue because whenever the dot product is negative, this corresponds to a setting where the camera is below the surface, in which case we do not expect to see any reflection from the light source. But in the case of the specular Phong model, the camera is still above the surface. So it's still possible for the camera to observe some light that's being reflected from the light source. Okay. So unfortunately, the Phong model has this artifact that's not able to correctly simulate the specular reflection in these particular configurations of the scene. So in order to fix this artifact, we have to look at some slightly more sophisticated specular models that don't exactly have that don't have the same issue as the Phong model. And one model that we can use to fix this artifact of the Phong model is the Bling-Phong specular model. With the Bling-Phong specular model, we're going to try to fix this artifact of the Phong model by changing the way that we compute the dot product. For the Phong model, the dot product is computed between the reflection vector and the view vector. But in the case of the Bling-Phong model, this dot product is replaced with a dot product between the normal vector and this new half-wave vector h. So to illustrate how this Bling-Phong model works, let's say we have a configuration of the scene that looks like this. We calculate our reflection vector by reflecting the light vector along the normal direction. This half vector h is going to be defined as the average vector between the wait, sorry. Sorry. So this reflection vector is going to be this half vector is going to be determined as the average vector between the view vector and the light vector. So this vector is going to lie halfway between the view vector and the light vector. And we can calculate this half vector by simply adding the light vector with the view vector and then normalizing that vector back to a unit vector. And this will give us a vector that's halfway between those two directions. So this is a little bit of a strange vector. And we are going to use this to calculate our dot product instead of using the reflection vector. Okay, so this might seem a little bit strange at first, but let's go through the behavior of this half vector under different configurations of the scene. So let's say the camera was exactly along the reflection direction. So the view vector and the reflection vector are perfectly aligned. With the Phong model, this is the configuration of the camera where we would expect there to be the maximum specular reflection because the camera is looking exactly along the reflection vector. With this particular configuration of the scene, when we compute the average between the light vector and the view vector, we're going to get a half vector that's exactly aligned with the normal direction. So because the reflection vector is the reflection of the light vector along the normal, if the view vector is equal to the reflection vector, then the half vector will also be aligned with the normal vector. Which means that in this case, when we compute the dot product between the half vector and the normal vector, we're going to get the maximum value of 1. Which means that whenever the reflection vector aligns with the view vector, we're going to get the maximum specular reflection from this Bling-Phong model, which is consistent with our expectation from the Phong model as well. So this seems to check out. But now let's see what happens when we move the camera away from the reflection vector. As the view vector moves further and further away from the reflection vector, the half vector is also going to move further and further away from the normal vector. So in this case, we're going to, as the camera moves away from the reflection direction, the dot product is also going to decrease in value, which means that we are going to see a less and less intense specular reflection as the camera moves away from the reflection vector. So this is also consistent with our expectation of what should happen with these specular reflections. So in this case, the behavior is still consistent with the Phong model. So far, everything looks good. But next, let's take a look at what happens in the more extreme configuration that we saw earlier. So in this configuration, the angle between the view vector and the reflection vector is greater than 90 degrees. Under the Phong model, this will be the situation where we get a negative dot product, which would then be clamped to a value of 0. So in this configuration, under the Phong model, we are not going to observe any specular reflection from the specular model. But now, let's say we compute the half vector between the light vector and the view vector. This is going to give us a half vector that's roughly pointing along this particular direction. And now when we compute the dot product between the half vector and the normal vector, the angle between the half vector and the normal vector is now less than 90 degrees. So when we compute the dot product between these two vectors, we get a positive value instead of a negative value, which means that it's not going to be clamped to 0, even in this more extreme configuration of the scene. We're still going to observe some specular reflection under the Blink-Phong model, where we will have observed a 0 specular reflection from the Phong model. Okay. So with this adjustment, by computing the dot product between this new half vector and the normal vector, we can now fix this artifact from the Phong model, where whenever the reflection vector and the view vector, is more than 90 degrees apart, the Phong model will give us a 0 specular reflection, but the Blink-Phong model will still allow us to observe some specular reflection in these more extreme configurations. And this can then fix the visual artifacts that we observed from the Phong model previously. In the case of the Phong model on the left, for these very rough surfaces, we can see a sharp cutoff in the specular reflection in some of these more extreme configurations of the camera. But in the case of the Blink-Phong model, even under these more extreme configurations, we can still see a nice smooth fall in the specular reflection that doesn't have this sharp, unrealistic cutoff. So with the Blink-Phong model, we're able to produce a more realistic specular highlight for some of these rougher, more diffuse surfaces with a low shininess value. And in practice, the Blink-Phong model is probably is used a bit more commonly compared to the Phong model, because of some of these artifacts of the original Phong model. Okay. So any questions about this Blink-Phong model? It's just a very small change to the Phong model. It just changes the dot product. It's then able to give us a more realistic rendering of these specular reflections. Okay. Any questions about this? Okay. Well, if there are no other questions, then we are going to wrap up by discussing one little detail that we've kind of glossed over so far. We've introduced a bunch of different lighting models that we can use to determine the color that we should assign a particular point in the scene. But now, when we apply these lighting models, one of the decisions that we have to make is which points do we evaluate these lighting models at? So there are kind of a bunch of different design choices that we can make for where we apply these lighting models. So for example, one simple strategy that we can use is that we'll only evaluate these lighting models once per polygon in our mesh. So let's say if our mesh was made up of a bunch of triangles, we can evaluate the lighting model once for each triangle. And then we can assign a constant color over the surface of the triangle. So with this flash shading technique, let's say we might evaluate the lighting model at the center of a triangle. And then we are going to assign that same color across the whole surface of that triangle. Now, this is a very simple strategy for applying this lighting model, but it can lead to some visually jarring artifacts. On the right, we have an example of a sphere that was colored in using this flash shading method. And we end up seeing very sharp discontinuities between adjacent triangles because every triangle has flat color, and every time we move to a different triangle, the color might change drastically from triangle to triangle. So instead of seeing a nice, smooth spherical surface, we end up seeing these very jagged results instead. So this flat shading method might not necessarily give us very realistic results. Now, one way that we can get a smoother result is by using a slightly better shading technique called Garot shading. And with Garot shading, we're going to evaluate the lighting model once for every vertex in our mesh. And then we're going to interpolate the colors at the vertices to every point inside a triangle. So in this case, we might just calculate the color for every vertex, and then we can use barycentric interpolation in order to interpolate the colors at the vertices to all the points inside each triangle. And this Garot shading technique can then give us a smoother appearance compared to flat shading. Now, while Garot shading can give us smoother results, it might be a little bit hard to see on the slide, but if you look very closely, you can see that there are still some visual artifacts from this Garot shading method. In particular, the highlight on the sphere should appear fairly smooth and round. But if you look closely enough, you can see that there's kind of these starbursts, these sharp edges at the highlight of the sphere. And this is an artifact that's produced by barycentric interpolation. Because we only calculate the lighting values at the vertices and we interpolate those values to the interior points inside triangle, these interpolated values can end up leading to some discontinuous effects between adjacent triangles. Okay. So Garot shading is a little bit better, but it can still lead to some visual artifacts. So if we want the best results, the alternative method that we can use is by using Phong shading. And the idea with Phong shading is that we're going to apply the lighting model once to every pixel that we color in our image. So for every pixel in our image, we can always find the corresponding point on the surface of an object. And we'll just apply the lighting model to that particular point on our object to determine the color for a given pixel. And we'll repeat this calculation for every pixel in our image. So rather than relying on interpolation to get the color for each pixel, we will just simply evaluate the lighting model for every single pixel. This is a much more expensive method, but it can give us the best quality results. So in the case of the sphere on the right here, with Phong shading, we see a nice smooth spherical highlight at the top of the sphere. So Phong shading would typically give you the highest quality results, but it does come at the additional cost of having to evaluate the lighting model for every pixel, which can become a bit expensive. But nowadays, with hardware accelerators like GPUs, which can massively parallelize calculations across many compute cores, implementing the Phong model is actually not too slow. We can parallelize a lot of these lighting calculations for every single pixel across lots of cores on the GPU. So you can still implement Phong shading in real time with hardware acceleration. But if you are working in a very compute-constrained application, then some of the more efficient methods like Garot shading or flat shading may in fact still be a reasonable choice. So for most rendering pipelines that use hardware accelerators like GPU, most of the time they'll implement Phong shading. Okay, yeah. So these are some of the different shading techniques that we can use to apply these lighting models. Any questions about any of this? Yep.
Keyframe function and filter the same the right column, or are they separate terms?
They're different terms. So these are typically referred to as shading methods. So you can think of these shading methods as determining how you apply a particular lighting model. So in this case, all flat shading, Gouraud shading, and Phong shading, they just differ in terms of where we apply the lighting models. Any other questions? Okay, so this is everything that I want to discuss for lighting models. And at this point, you probably have enough to complete most of assignment 4. So for assignment 4, we will ask you to implement some of these different lighting models that we discussed, along with some texturing that we're going to cover in the next lecture. Assignment 4 is going to be due in roughly 2 weeks from now, and it's much more involved compared to assignment 3. So definitely try to get an early start on assignment 4 if you can. So you should have enough to implement some of the shading models for that particular assignment. Now, when implementing assignment 4, there are some details to watch out for, especially when it comes to implementing these shading models. So try to get started on that early, since it's easy for there to be little bugs that take some time to fix. Okay, since we still have a bit of time, then let's get started on the next topic, which is going to be texture mapping. So for this particular lecture, we're going to take a look at what textures are and what are some of the scenarios where we would want to use textures. We'll then introduce some different techniques for mapping textures onto the surface of an object. And then we'll go into some of the implementation details that are important for correctly implementing texture mapping. So to start, let's take a look at what are textures. We can think of textures as a way of representing detailed surface patterns on the surface of an object. So for example, let's say I want to render spheres that are made with different materials. So we might have a sphere that's covered in a checkerboard pattern. We might have a sphere that's made of bricks, a sphere that's made of wood, or a sphere that's covered in grass. So how will we render these different spheres that are made of these different types of materials? So one way that we can go about modeling these different types of materials is that we can try to model these materials geometrically by using a mesh to model all the different surface details that we observe from these different materials. So for example, we might use a mesh to model all the detailed crevices of the bricks, all the little bumps in the bricks. Or we can use a mesh to model all the grass that's on the surface of our sphere. And in that case, let's say we might have a very detailed mesh for modeling all the individual blades of grass that's on the surface of our object. So if you want to model all these detailed surface patterns geometrically, this might be extremely expensive. We might have to use a very high resolution mesh that contains lots of vertices and triangles in order to model all the little bumps and crevices on the surface of our object. So trying to represent these detailed surface patterns geometrically can be very expensive, both in terms of storage, because we have to store a very high resolution mesh, as well as very slow in terms of actually rendering that complex mesh, because we might have thousands of millions of triangles that we're going to have to render on the surface of these objects. So trying to brute force represent these geometric details using a mesh is not very practical in practice. And this is where textures come in. The idea with textures is that rather than storing rather than representing these surface details geometrically, we can simply represent these surface patterns with an image, with a texture. And right. So we can just represent these patterns as an image, and then we can project that image onto the surface of our object, and then use that to give the object the appearance of the different types of materials. So in this case, we can just have the same simple spherical mesh for all of these different spheres, and we just have to apply a different image, a different texture on each of the spheres in order to make it look like these objects are made with different materials. So this then allows us to represent fairly complex surface details very efficiently using an image instead of having to resort to using a very complex mesh. Okay, now a little bit of terminology when we are working with textures. When we are referring to images, we refer to the individual elements of that image as a pixel. In the case of textures, we are going to use a slightly different terminology, where we are going to refer to the individual elements of a texture as a texel or a texture element. But you can just think of texels as exactly the same as pixels. They're just a point on an image. So a texture is really just exactly the same as an image, but we use this different terminology in order to avoid some confusion when we are working with both images and textures at the same time. Okay, but otherwise, you can just think of textures as just an image. Okay, I guess any questions about this? Any questions about like why we might want to use textures? Okay. So let's say if we have a texture that represents a surface pattern that we want to apply to the surface of an object. The key challenge then is how do we map a 2D texture onto the surface of a 3D shape? So the process of mapping a 2D texture onto a 3D surface is referred to as texture mapping. So let's say if I want to render an object with a checkerboard pattern on its surface, then we are going to have to take a texture of a checkerboard and somehow map each point on the 3D object onto a point on our 2D texture. So the challenge of texture mapping is somehow to construct this correspondence between points on a 3D object to points on a 2D texture. And a simple way that we can perform this kind of projection is by using a simple intermediate geometric shape. So for example, let's say we have a 3D object and I want to map the texture onto the surface of that 3D shape. So I have to somehow convert 3D points on the object onto 2D coordinates for our texture. Okay, so a simple way that we can do this is by using planar projection. Our texture is just represented by a plane, and I want to project 3D points onto that plane. So the simple way that we can do this is that we can just take a 3D point, and we can just remove one of the components and use the remaining two components as the 2D coordinates for our texture. So for example, let's say if I want to project all of the points onto the XY plane, then I can simply remove the Z component and use the XY coordinates of the 3D point as the UV coordinates, as the texture coordinates for my 2D texture. So in this case, I can take XYZ, I can map that to the UV texture coordinates, and then I can use the UV coordinates to look up a color from my texture. Okay. So this planar projection method is a very simple way of mapping 3D points onto a 2D plane. And it can work well for some shapes, but it can also lead to some visually jarring artifacts. So for this cube and this sphere, if we look at the texture pattern on the top of these objects, they look fairly reasonable. But if you look at the texture pattern on the sides of the objects, we end up seeing very large distortions that end up leading to a pattern that no longer looks like the original checkerboard pattern that we started with. So as we move towards the size of the object, we see large distortions in the texture. Okay. Now, one way that we can try to fix this artifacts with planar projection is to use a slightly more complex intermediate shape to perform that projection. So for example, we can, instead of projecting everything onto a plane, we can instead project things onto a cylinder. And you can think of this as kind of like taking a texture and wrapping it around the object. And then we are going to map 3D points on the object onto the surface of the cylinder that's wrapped around the object. And we can use that to determine the 2D texture coordinates for sampling from our texture. This cylindrical projection leads to some better results on the sides of the objects. But now if you look at the top of the objects, you can still see large distortions of the checkerboard pattern. And in general, we can use more and more complex geometric shapes as well. So instead of using a cylinder, we can use spherical projection, where we project points onto a sphere, and we use the coordinates on the sphere as the texture coordinates for sampling from our texture. So with spherical projection, we can get more reasonable results for something like the sphere, but we can still see some distortions in the checkerboard pattern for something like a cube, like at the top and the bottom of the cube. So in general, for these simple projection methods, if the underlying shape is, if the 3D shape is fairly similar to the intermediate shape that we're using for performing that projection, then we can get fairly reasonable results. But if the 3D shape is very different from the intermediate shape that we use for the projection, then this can end up leading to large distortions in the texture, in the patterns in the original texture. So these simple geometric projection methods can be applied if we have relatively simple shapes. But if we have more complex objects, then unfortunately, most of these simple projection methods would generally lead to fairly large distortions in the texture patterns. So for texture mapping for more complex objects, we often have to rely on more sophisticated texture mapping techniques. And we probably don't quite have enough time to go over that for this lecture. So we'll probably wrap things up here. But I guess any questions about these simple projection methods before we conclude for today? Okay, if not, then we'll wrap things up here for today. Friday is going to be a holiday, so there's no lectures. So we'll resume this on next Wednesday's lecture instead. Okay, I'll see you next week.